So the speed is ds dt, and the tangent vector is t hat. And that's how we get this. Okay. So let's try just to see why dr ds should be t. Well, let's think of dr ds. Dr ds means, position vector r means you have the origin, which is somewhere out there, and the vector r is here. So dr ds means we move by a small amount delta s along the trajectory, by a certain distance delta s. And we look at how the position vector changes. Well, we'll have a small change. Let me call that vector delta r, corresponding to the size, corresponding to the length delta s. And now, delta r should be essentially roughly equal to, well, its direction will be tangent to the trajectory. If I take a small enough interval, then the motion will be almost tangent to the trajectory, times the length of it will be delta s, the distance that I have traveled. Okay, maybe I should re-explain that on a separate board. Okay, so let's say that we have an amount of time delta t. So let's zoom into that curve. Okay, so we have r at time t. We have r at time t plus delta t. This vector here I will call delta r. The length of this vector is delta s. And the direction is essentially that of the tangent vector. Okay. So delta s over delta t, that's the amount, that's the distance traveled divided by the time. That's going to be close to the speed. And delta r is approximately t times delta s. So now if I divide both sides by delta t, I get this. And if I take the limit as delta t tends to 0, then I get the same formula with the derivatives and with an equality instead of an approximation. The approximation becomes better and better if I go to smaller intervals. Okay, are there any questions about this? Yes?
So the direction, it was the tangent to the curve, right? You said like when you draw your two vectors at angle t and then t plus delta t, the resulting vector was tangent?
Yes, that's correct. So, okay, so let's be more careful, actually. So you're asking about whether the delta r is actually strictly tangent to the curve, is that?
First time around the other side of that bottom curve, and your second time is somewhere else, it wouldn't be tangent to much thing.
That's correct. Actually, delta r is not strictly tangent to anything. So maybe I should draw another picture. If I'm going from here to here, then delta r is going to be this arc inside the curve, while the tangent vector will be going in this direction. Okay? So they're not strictly parallel to each other, and that's why it's only approximately equal. Similarly, this distance, the length of delta r is not exactly the length along the curve. It's actually a bit shorter. But if you imagine a smaller and smaller portion of the curve, then this effect of the curve being a curve and not a straight line becomes more and more negligible. If you zoom into the curve sufficiently, then it looks more and more like a straight line, and then what I said becomes true in the limit. Okay? Any other questions? No? Okay. So what happens next? Okay, so let me show you a nice example of why we might want to use vectors to study parametric curves. Because after all, a lot of what's here you can just do in coordinates, and we don't really need vectors. Well, actually, vectors being a language, you never strictly need it, but it's useful to have a notion of vectors. So I want to tell you a bit about Kepler's second law of celestial mechanics. So that goes back to 1609, so that's not exactly recent news, okay? But still, I think it's a very interesting example of why you might want to use vector methods to analyze motions. So what happened back then is Kepler was trying to observe the motion of planets in the sky and trying to come up with general explanations of how they move. Before him, people were saying, well, they kind of move in a circle, but maybe it's more complicated than that. We need to add smaller circular motions on top of each other and so on. They had more and more complicated theories. And then Kepler came with these laws that said, basically, that planets move in an ellipse around the sun, and that they move in a very specific way along that ellipse. So there's actually 3 laws, but let me just tell you about the second one that has a very nice vector interpretation. So what Kepler's second law says is that the motion of planets is, first of all, they move in a plane, and second, the area swept out by the line from the sun to the planet is swept at constant time.